Hi everyone, welcome to the lecture series on power system analysis. Last class we discussed about how to model a power system, and we discussed about what is a per phase analysis, what is a per unit analysis, and how to model a three-phase system by using the per unit analysis. Today we are going to discuss about a very important topic in power system analysis. We call it as a power flow analysis. Power flow analysis. What is meant by power flow analysis? What is the need for the power flow analysis? Normally, when you're going for the power systems, we come across very big networks. It is classified as transmission networks and distribution networks. And normally, if you are run the power flow analysis, we can able to find all the unknown state variables with respect to the given network. The main purpose of power flow analysis, or we call it as a load flow analysis, is to find the unknown state variables in power system. So when you take a simple power system network, I took a 4-bus system. All these buses are interconnected. Let us take this is bus number 1, this is bus number 2, this is bus number 3, and this is bus number 4. I am connecting a generator at bus number 1. I am connecting one more generator at bus number 2. I am connecting some loads on bus number 3 and bus number 4. Okay. Then before discuss about how to do the power flow analysis for the given network, we are supposed to know what are the classification of buses in power system. So normally in power system, the buses classified into 3 types. The first we call it as a slack bus, or I can call it as a reference bus. The second bus we call it as a PQ bus, or I call it as a load bus. And the third bus normally we call it as a PV bus, or it is also called as a voltage controlled bus, or we call it as a generator bus. Okay. What is this slack bus, what is a PQ bus, and what is a PV bus? Actually these buses are classified based on the what is the parameter known at the particular bus. For example, when you're going for the slack bus, normally we know what is the voltage magnitude and what is the voltage angle. This is two important known parameters with respect to the slack bus, or we normally call it reference bus. When you're going for any big power system network, we have only one slack bus or one reference bus. And the main objective of this reference bus is to allocate the losses after the load flow is performed, the load flow is completed. Okay, it is used as a compensation bus. It is balancing the both real power and reactive power. And in slack bus, the two variable which is unknown is the real power P and the reactive power Q. Similarly, when you're going for the PQ bus or load bus, I know what is my real power P, what is my reactive power Q. I supposed to find what is my voltage magnitude and what is the voltage angle del. When you're going for the PV bus or generator bus, it is similar to the slack bus. In PV bus also we have the generator, but normally in PV bus I know what is the real power P and what is my voltage magnitude modulus V, and I don't know what is my Q and what is my del. Okay, so these variables I call it as a known variables. These variables I call it as a and unknown variables. Okay, so these are the basic classification of buses. If you want to study about the power flow analysis, we supposed to understand about what are the different type of buses available and what are the different parameters is known and what are the parameters we need to find. Okay, now what is the need for the power flow analysis? I clearly told of the main objective of the power flow analysis is to find the unknown state variables with respect to the different type of buses. So now we know that we have three type of buses, and you can see that I have certain variables are known with respect to the all the three buses, and certain variables are unknown we supposed to find. If you want to find these unknown variables, we supposed to run the power flow analysis. But before going to study in deep about power flow analysis, we need to derive the equation for the power flow equations, right? Because once you got the power flow equations in both polar and rectangular form, then by using the different numerical methods, we can able to find the solutions, right? I hope you understand what is the need for the power flow analysis, and what are the classification of buses, and what is the known and unknown variables, state variables with respect to the power system networks. Let us consider n bus network, right? Let us consider n bus network. So I'll draw the network for the n bus network. So this is my ith bus, and all these buses. This is bus number 1, and this is bus number 2. This will go up to the nth bus. The ith bus is connected to the nth bus. Okay. So let us assuming that the voltage at the ith bus, I call it is a Vi. Similarly, the voltage at the first bus V1, voltage at the second bus V2, and voltage at the nth bus is Vn. At bus I, we are injecting the power II. Okay. Let's consider in bus I we have many generators. We're injecting the current II into the ith bus. Then we know that the current flow in this line is I1, the current flow in this line is II2, and the current flow in the nth line is IIN. Now we are applying the Kirchhoff current law at bus number I can able to write the total current injected II is equal to II1 plus II2. This will go up to nth bus IIN. Okay. Now I can able to calculate what is my current in terms of the admittances, right? So I can write II is equal to, what is II1? II1 is nothing but, what is II1? II1 is nothing but what is the current flow between the ith bus and the bus number 1. I can able to write this is Vi minus V1 into the admittance of the line, right? So let us consider y small yi1 is admittance between the uh, bus 1 and sorry, bus I and bus 1. Then similarly yi2, this will go up to yin. Now I can write this is equal to yi1. Instead of ii2, I can write vi minus v2 into yi2. This will go up to the nth bus, and Vi minus Vn into Yin. So now I collect the similar terms here. Vi is common, I'll take Vi outside, then I can write yi1 plus yi2, this will go to I2 Yin. Then remaining terms minus V1 yi1 minus V2 yi2, and this will go up to Vn Yin. When look at this term, this yi1 plus yi2, this I can able to write as a summation series. So this is equal to Vi sigma Vi sigma j is equal to 1 to n. Okay. Actually, in this diagram, we can also use include the self admittance of the network, and let us consider the self admittance of this line is yi naught, and the current flow in this line, I say it is a ii 0, and this is iin. Then I can write this is equal to, I'll add one more term here, so that this equation will be completed, right? So this is vi into yi0, am I right? So this is vi into yi0, so I can include that term here plus vi into yi0. Okay, then I can write, when you take vi outside, this is plus yi0, I hope it's correct, right? Plus yi0, it become j is equal to 0 to n yij, because j is running from 0 to n, so yij, right, into vj. So this term represent the summation series, and similarly the second term I can write minus sigma j is equal to 1 to n yij into vj, right? So when you are substituting j is running from 1 to n, when j is equal to 1, I'll get the first term vi1 into v1. The same thing applied for all the buses up to nth bus. So this I call it as a ii. Okay, so now I get the equation for the current injected into the bus ii in terms of voltage magnitude and the admittances, and from this we can able to find what is the uh, power flow equations. Okay, we know that the complex power, okay, the complex power pi plus jqi, that is equal to vi into I conjugate. We know that normally most of the load are inductive load, then I can able to represent my power as vi conjugate. In case if you are dealing with a capacitive load, then I can put v conjugate I, but most of the loads are inductive nature, then I can able to write the power flow equations pi plus jqi is equal to vi plus ia conjugate. Now in this equation I want to find what is the equation for a ii, then I can write my ii is equal to, so this is ia conjugate, right? This is equal to pi plus jqi by vi. If you find what is the ii, take the conjugate on right hand side, then this pi plus jqi become pi minus jqi, this divided by vi conjugate. Okay, so this equation, this is a equation for current ii in terms of the real reactive power and the voltage. We already derived the equation for ii. Then I can able to substitute these equations back into the equation for ii. Okay, now I substitute the ii from this equation, then I can write vi sigma j is running from 0 to n yij minus sigma j is equal to 1 to n yij vj, this is equal to pi minus jqi divided by vi conjugate. Okay, now I can take this vi conjugate to the left hand side. I can write vi conjugate this into Vi sigma j is equal to 0 to n Yij, then minus sigma j is equal to 1 to n Yij into Vj, right? This is equal to Pi minus Jqi. Actually, our objective is to find what is the equation for the real power and reactive power. When you're comparing the real and the imaginary component of the left hand side and right hand side, you can find what is your real power and reactive power. And from the above this equation, I can write Pi is equal to real of Vi conjugate this into Vi sigma j is equal to 0 to n Yij minus sigma j is equal to 1 to n Yij into Vj. I close this bracket. Okay. So this is the equation for the real power Pi. Similarly, if you are compare the imaginary components of left hand side and right hand side, I can write Qi is equal to minus, because we have minus here. So minus imaginary of, you take this term Vi conjugate Vi sigma j is equal to running from 0 to n Yij minus sigma j is equal to 1 to n Yij into Vj. Okay. So these two equations, we call it as the power flow equations, but actually these equations are written in Cartesian form, right? If you want to find the solution for the power flow equations, we can use this form of equation, or the methods like Newton Raphson, they are using the polar based equations. Then you need to convert this same equations in polar. So this is a very simple power flow equations. Okay. So if you want to get the solution for the power flow problems, we need to solve this power flow equations. Okay. Now let us rewrite the same equations, right? This equations in Cartesian form. I won't write the same thing in polar equations, right? How we can do that? So we know that I said your Pi minus Jqi that's equal to Vi conjugate into Ii. Okay, Vi conjugate into Ii. Now you just convert this equation, right, in polar form. Then I can write your Pi minus Jqi, that's equal to, I'll write Vi. Let us take Vi. Vi is equal to modulus Vi angle del. This del I call it as a voltage angle. Okay. Then I can write this is equal to minus del this into Ii. Okay, this into Ii. Is that clear? So I just because Vi is equal to modulus V into del, I just take the conjugate. I'll put a minus sign for this equation, this angle. Now I can write the same power flow equations in polar form. My Pi is equal to sigma j is equal to 1 to n. Okay, modulus Vi Vj Yij cos of theta ij plus del j minus del I. Okay, so this is a equation for the real power in polar terms, because I convert this equation, rectangle equation, into the polar equation. Similarly, I can write the equation for reactive power Qi, that's equal to minus sigma j is equal to 1 to n Vj, sorry, Vi Vj yij, then sine of theta ij plus del j minus del I. Okay, so we derive the power flow equations in rectangular form as well as in a polar form. Okay, so you may ask, what is the need for deriving the equations in both rectangular form and polar form? Because we have many methods to solve the power flow equations. Mainly, we are using the two important methods for getting the solution for the power flow equations. The first method, we call it as a Gauss-Seidel method. The second method, we call it as a Newton option, right? These are the two important methods used for getting the solution for the power flow equations. So Newton option method, again, it is simplified as a fast decouple method. Okay, fast decouple method. So normally this Gauss-Seidel method using the rectangular form of the power flow equations, and Newton option method using the polar form of the power flow equations. Okay, so both these methods are numerical methods, or we call it as iterative based methods. So once if you want to get the solution for the power flow equations, we'll start up with the initial value when you slowly progress into the iterations, and when you're reaching the final solutions, then your solution is converged. Okay, so for that only we need the two forms of the power flow equations. I hope you understand what is power flow analysis, uh, what is the power flow equations, how to derive the power flow equations in both polar form and rectangular form, and we also introduced about what are the methods available to get the solution for the power flow equation. Okay, thank you. Let us see next class. ஏன் அது கட் ஆயிடுச்சு? அது நிறுத்திடுவா? இல்லை நிறுத்தி நெக்ஸ்ட் இது போகிறேன். ஐயோ இதெல்லாம் கட் பண்ணிக்கலாம்ல?